So experimental probabilities are fine if you want to actually do the experiment. And if you don't know some things about the object you're working with, then you might have to actually physically do the experiment. But if there are times where it's nice to be able to just calculate the experiment. So I want to talk about in this section, how do we actually calculate probabilities? And there's one that we know as theoretical probabilities. So this is in theory, what you think that probability should be. And the first thing we have to do is we have to define what are equally likely outcomes. Equally likely outcomes are where each outcome of an experiment has the same chance of happening. And I want to point out these are the outcomes, not an event. So you could have an event, but it's actually the outcomes we're looking at as being the same chance of happening. You can have different events that have different probabilities, but these are the actual outcomes, each individual outcome. So one of the things I like to talk about is if you're pulling same-side balls that are different colors out of a box, if you have more red than blue, some people think, well, you don't have equally likely outcomes because you have more red than blue. But each ball is your outcome. So each ball is, if they're the same side, are equally likely to come out. I don't care what color they are. When I go to put my hand in and pull one out, each ball is equally likely to come out. The probability of getting a blue ball over a red ball is different because there's more blue than red, but the outcomes are the actual balls themselves. Now, the problem with equally likely is you have to assume that you have equally likely outcomes, and sometimes that assumption is not the best assumption. So you have to be careful about this. It is a hard assumption sometimes to take. You have to think about the fact that what you think should happen only happens if they're equally likely outcomes. But if we have that, we can then calculate our theoretical probabilities. So the definition of a theoretical probability is that if the outcomes are equally likely, then the probability of an event is equal to the probability of the number of ways the event can happen over top of the number of ways the number of total outcomes. Another way to think of this is that it's the number of outcomes in the event space divided by the number of outcomes in the sample space. And so if you actually were to write out your sample space and write out your event space, then all you have to do is count. So people sit there and say that probabilities are really difficult because they find them hard, but they don't count. If you actually just counted, they'd be much easier and much faster to do. So it's a little bit longer sometimes. I shouldn't say much faster because sometimes it's long to write everything out, but it is much easier because you all know how to count. So let's take an experiment. Let's take an experiment. We're going to flip a coin twice. So what I want you to do is I want you to think about what that sample space would be. And remember, the outcomes have to be equally likely. So some people think that they can write down your sample space is a collection of, let's say, you get 0 heads, 1 head, and 2 heads. And that seems like a perfectly nice looking sample space. But the problem is there are more ways of getting a 1 than there is of getting a 0 or 2. So these outcomes are not equally likely because I can get a 1 more ways than getting a 0 and a 2. So this is not equally likely. So we can't use that as our sample space. So let's try a different sample space. Maybe instead of listing how many heads I might get, let's list maybe what I got in each roll. So I could flip a coin. The first time I flipped the coin, I could get a head. The second time I flipped the coin, I could also get a head. So one time of doing the experiment, I could get a head, and that's one outcome of the experiment. because my experiment is flipping a coin twice. The second time another time I can do the experiment, I could get a head the first time and a tail the second time. So there's another outcome. These are both the heads and tails because we're dealing with flipping a coin twice, but you can do other experiments where you're doing something twice. They don't have to be the exact same thing each time, so you're still going to list all the different combinations you can get. You could flip the coin and get a tail first and then a head, or you could flip the coin and get a tail and then a tail. And that appears to be all of our outcomes. So now let's ask, are these equally likely? Is it just as likely that you get a head-head as it is for you to get a head-tail? And yes, there's nothing that makes it one different than the other. So these are equally likely, so we can use this as our sample space. So now let's find some probabilities. Let's find the probability of getting two tails. So the first thing I want to do is I want to write out what is that event space? What are the ways of getting two tails? So that means, and I'm going to go back to that sample space I have. Remember, these are my 4 outcomes. So when I'm talking about getting two tails, those two tails have to come from one of these 4 things in here. If they don't, then you don't have the right sample space. So what I notice is that two tails would be getting a tail and a tail. So I've just, by putting it this way, I've just listed my event space, and I can now see I have one thing in this, and there's 4 things in the sample space. So my probability is 1 out of 4. I don't reduce, I don't make it into a decimal, I leave them just like this. Now we want to get a tail and a head. So this would be the probability, again, I want to write out my sample, my event space. I want a tail and a head, so I can get a tail and then a head. I never said I had to get a head in that order, so I could also have gotten a head and then a tail. But I did want to get a tail and a head, so it has to be just these 2. So now I can go and count. There's 1, 2 out of the 4 things we had. Again, I don't reduce this. I leave it as 2/4. The main reason I leave it as 2/4 is because now I know there's 2 ways out of the 4 ways this can happen. I can easily compare this 2/4 to the 1/4. 2/4 is bigger than 1/4, so therefore I know this is more likely to happen. Getting a tail and a head is more likely to happen than getting 2 tails. So that's the other reason I don't reduce. Makes life a little bit easier to find these probabilities and compare. But I like the idea that I know this is 2 ways out of 4. I wouldn't see that as well with the 1/2. Now let's look at getting at least one head. I'm sorry, at least one tail. So at least one tail means I'm going to get a tail and a head. That's one tail. A head and a tail, that's another tail. But at least means that many or more. So I could also have gotten 2 tails. So now I know I get 3 ways because I can count 1, 2, 3 divided by 4. So I realize writing these out makes you think, well, I don't need to do that. But they do get more complicated. And again, you can't get probability wrong if you list it and then just count. The probabilities will always be correct. All right, let's try another. Let's keep going. Let's try doing a tail or a head. Now a tail or a head, or means one or the other. So we're going to go with tail or a head means you're going to get a head tail or a tail head. So that was the same as getting one tail, and that's okay. You can have 2 events that say different things, but get you the same outcomes. Still 2 out of 4 is your probability. Now, the next one I want to do is getting a back. And you're like, what the heck, a back? But I go back to my sample space, back at my sample space, I see head, 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 tail, tail, head, tail, tail. I don't see back. So there are no outcomes in the sample space that will do that. So therefore, this event space would be empty. There'd be nothing there. So that means my probability is 0 out of 4. This one I usually do reduce to 0. I want to do one more. I want to do the probability of getting a tail Actually, wait a second. No, I don't want to do one more. I'm going back to this one here. Just a second. Tail or head. I could have also gotten two tails. I didn't say just one tail and one head. I said tail or head. I could have gotten two tails. So I actually did this one wrong. Let's fix it. I could have gotten two tails. I also could get two heads. So that is actually 4 out of 4. And again, this is one I probably would reduce to 1. This example gives us some properties of probabilities I want to list on. The first one is I want to point out that all of my probabilities, the smallest probability I saw was 0, the biggest probability I saw was 1, and all the other ones were somewhere between 0 and 1. So therefore, my properties of a probability is the probabilities are always less than or equal to. The probability is always less than or equal to, greater than or equal to 0 and less than or equal to 1. So you always see your probability values somewhere between those. I will point out that if the probability of an event equals 1, that means it will happen. There's no way it cannot happen. If your probability of an event is actually equal to 1, then it is a certain event. Certain event. It will happen. So if you know the probability of it raining today is 1 or 100%, then it will actually rain today. There's no questions. That's why you don't normally see that. If the probability of an event equals 0, then it's called an impossible event. It means it can't happen. So again, if you know the probability of it raining today is 0, then you know it will not rain today. Let's do another example, another experiment. We're going to pull a card from a standard deck with no jokers, and I want to state the sample space. So the sample space in this case is to list every single solitary card. Don't try to do anything more than just list all your cards. So you have a 2 of spades, a 3 of spades, a 4 of spades, 5 of spades, 6 of spades, a 7 of spades, an 8 of spades, a 9 of spades, a 10 of spades, a jack of spades, a queen of spades, a king of spades, and an ace of spades. And then I can do the same thing with diamonds and clubs and so forth. So I have 2 clubs all the way up through and this is where people say, oh, I don't want to do all that. Well, I know you don't want to do all that, but it will make life much easier if you do all this because you can count. I know you know how to count. Then we also could have the 2 of hearts. And then the 2 of clubs. All right, and those are all your cards. There's 52 of them. There's 13 in each suit. I do want to also point out that I usually play cards when the ace is the high card. So that's why I listed ace as a high card. Also, the jack, the queen, and the king have faces on them, so they're sometimes called face cards. The ace does not have a face on it, so it is not considered part of the face cards. So now let's go ahead and find the probability of a diamond. So again, what I want to do first is I want to list out the event space of getting a diamond card. So my event space would be listing all the diamonds. So 2 of diamonds, 3 of diamonds. Now I know what they all are, so I'm just going to do dot, 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 ace of diamonds. Because I have them all listed up here, I can kind of cheat a little bit here. Not really cheating, it's just making a simpler way to do it. I know there's 13 cards here. I know there's 52 cards here. Again, I can count, and I get 13 out of 52. Again, I don't reduce that. Let's do another one. Let's do the probability of a card is a 6. So again, I'm going to first list my event space. So I'm looking for the probability of getting a 6, which would be a 6 of diamonds, a 6 of clubs, a 6 of spades, and a 6 of hearts. That I can now count. There's 1, 2, 3, 4 out of the 52. And again, I don't reduce. I leave it just like that. Let's do a card of the club. So again, I would first list it. So we're looking for the probability of all the clubs. So it'd be a 2 club. And again, I'm going to cheat a little bit and not list them all. I know that there's 13 cards there. I'm not going to write every single one, but I should write every single one and count. But I have listed them all. I just have the dot, dot, dot. So now I want to talk about what's the probability of getting not a club. So not getting a club, that would mean it's every other card that's not there. So it's the probability of a 2 of diamonds all the way through the ace of diamonds. Again, there's 13 cards there. There'd be the 2 of spades all the way through the ace of spades. And a 2 of hearts all the way through the ace of hearts. So I have listed them all. There's 13, 26, 39. So there's 39 out of 52. Let's do a diamond or a club. So we're looking for the probability of a diamond or a club. So or means one or the other. So again, I'm going to list out my event space. My event space would be all the clubs. So 2 clubs through the ace of clubs. And 2 of diamonds would be the other one through the ace of diamonds. And again, that's 2 of diamonds to the ace of diamonds. The ace of clubs is 13. 2 of diamonds to the ace of diamonds, that's again 13. So 13 and 13 is 26. So it's 26 out of 52. How about a club and a diamond? So again, I'm going to list all the different ways that this event can happen. So I need to pick one card. Remember, my experiment is to pick one card from a deck. So I'm picking one card from the deck. That card cannot at the same time be a club and a diamond at the exact same time. So there are no cards in there. So that means we have an empty set and there's 0 things in there out of 52. Again, I normally do reduce that one to 0. All right, let's do club or 6. So again, I'm looking at my event space. My event space would be all the clubs. So 2 clubs through the ace of clubs, and then a 6. So I would have the 2 of diamonds, the 6 of diamonds, the 6 of hearts, and the 6 of spades. But I don't want to list the 6 of clubs again because I already have the 6 of clubs in this listing. So if I listed it again, I'd be listing it twice, and I don't want to list it twice. I only want to list things one time. I only want this list in your event spaces, each outcome that can happen. It doesn't matter where it happens, and you don't want to list it more than one time because you're counting. So there's 13 here, 14, 15, 16. So there's 16 out of 52. Now let's do a club and a 6. So this would be the probability of getting, again, looking at my event space, this is getting a club and a 6, so it's the 6 of clubs. It's the only way I can get a club and a 6 at the exact same time. There's only 1 out of the 52. So there's a couple concepts I want to talk about that we saw in this example. First off, the probability of a club and a diamond. Did that equal the probability of club plus the probability of diamond? Well, let's see. the probability of a club and diamond. Sorry, there should be or diamond. This one should also be or. So probability of a club or diamond. So let's go back and look what those probabilities were. Probability of a club or diamond was 26 out of 52. This is the probability of a club. Looking at the probability of a club, that was, back over here, the probability of a club was 13 out of 52. And the probability of a diamond was also 13 out of 52. And notice 13 out of 52 plus 13 out of 52 does in fact add up to 26 out of 52. So yes, they do actually equal. Hey, that's great. It looks like we can do or statements by just adding these two probabilities together. So let's see if it works here. So probability of a club or 6, we're going back over here, probability of a club or 6 was 16 out of 52. And the probability of a club, we already know, is 13 out of 52. And the probability of a 6, we just remember we already calculated this when that was 4 out of 52. Oh, wait a second. 13 out of 52 plus 4 out of 52 is 17 out of 52. But that's not the same as 16 out of 52. So no, they don't equal. So I wonder why sometimes we can do or statements when they do actually, we can just add them together, and sometimes we can't, and I wonder why that was. And so I want to point out to you that here in the club and diamond, there was no way for those to happen at the same time. They had no overlap. So therefore, they had nothing in common. Whereas a club or a 6 had something in common. They have the 6 of clubs in common. In fact, when we did the probability of club, it had all the clubs. We did the probability of 6, it had all the 6s, which means we just counted the 6 of clubs twice. We counted it here, and then we counted it over here. But when we did the probability of club or 6 by itself, we only had the 16 out of 52. We didn't count it twice. So the reason it didn't work is that this one had no overlap. And this one actually had some overlap. So that's where the problem came in, is if you have overlap, you can't add them together. When you don't have overlap, you can. The last thing I want to kind of just mention is the probability of club plus the probability of not a club. What did that equal? So remember, the probability of a club was 13 out of 52. The probability of not a club, if we need to, we can go back over here and look. Probability of not a club was 39 out of 52. So that's 39 out of 52. If I were to add those together, I would get 52 out of 52, which, by the way, is the number 1. So it looks like the probability of club plus the probability of not a club actually always gives you 1. All right, so there's a couple of things we got from here. The first one is that not a club and a club are what we call complementary events. Complementary events are a complement is the complement of A. If, and I'm going to say a complement, I'm going to give it some terminology so we can work things a little bit. One thing we can say is not A, or A with a little subscript C in it. So that's another notation we also can use. All right, so not A or a complement is the complement of A if not A contains everything in the sample space that is not in A. So in other words, not getting a club is the complement of getting a club, because not getting a club contained every card that was not a club. And that was everything that was in the sample space that was not a club. So that's the idea of a complement. When we have complementary events, the probability of A plus the probability of its complement, not A, is always going to give you 1. And where this is useful is if you know the probability of a complement, you can find the probability of the other event. So like if you know the probability of you getting the flu this year is 10%, or let's say 50%, then the probability of you not getting the flu would also be 50%. The probability of you getting the flu if you had the vaccine for the flu is about 30% or 40%. So the probability of getting the flu, if you have the flu shot, would be 1 minus 40% or 60%. Sorry, the other way around. The probability of not getting the flu, if you got the flu shot, would be 60%, 1 minus that. So we like to use these ideas. Mutually exclusive is the other concept I want to talk about. Mutually exclusive events is where two events, we'll call them A and B, are mutually exclusive if it is impossible for the two events to occur at the same time. In other words, there's no overlap in their event spaces. Their event spaces have nothing in common. And so this is another concept. They are not the same as complements because they're not saying it covers the whole sample space. It's just saying they can't occur at the same time. This brings us to what we call the addition rule in probability. And the addition rule, I don't usually use this rule very often, but a lot of people like it. And what it says is the probability of A or B is the probability of A plus the probability of B. But that might have had some overlap. So then we'd subtract off the overlap, and the overlap would be A and B. A and B are that overlap. So if you want to use this rule, you can. I prefer to just write things out and count. I don't like using these rules, but it's there if you want it. If A and B are mutually exclusive, then what you have is the probability of A or B is the probability of A plus the probability of B. So that's why the probability of a sum of a spade or club was just adding the two together, because those two events are what we call mutually exclusive. They can't happen at the same time. And if you notice, the probability of A and B is 0. So if the probability of A and B are 0, they're mutually exclusive. If they're mutually exclusive, then the probability of A and B is 0 also. So let's do one more experiment, and we're not going to do this whole experiment. We're just going to write out the sample space. This is an experiment of rolling 2 fair dice. So I want to write out the sample space to this. Again, your sample space would equal all the different outcomes. And again, you don't want to just list. You can get a sum of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So those are the different sums you can get when you roll a pair of dice. But it's way more likely you're going to roll a sum of 7 than you would a sum of 12. So these, again, are not equally likely. So you can't just write out the sums because they're not equally likely. So instead, we want to figure out the sample space. What we could do is kind of like with the dice. We could list, not with the coins, we could list what we could get on the first die. I could get a 1 on the first die and a 1 on the second die. A 1 on the first die and a 2 on the second die. A 1 on the first die and a 3 on the second die. A 1, then a 4, a 1, then a 5, and then a 1 and a 6. Or, and I kind of like to write these a little bit in a nice order, and get a 2, 1, a 2, 2, a 2, 3, a 2, 4, a 2, 5, and a 2, 6. Or I could get a 3, 1, a 3, 2, a 3, 3, a 3, 4, a 3, 5, and a 3, 6. Or I could get a 4, 1, 4, 2, 4, 3, a 4, 4, a 4, 5, and a 4, 6. And you can see the pattern here. I could get a 5, 1, a 5, 2. And you can write these any way you want. I just happen to have my way of writing them. I actually think they're easier to write out than it is to type out. And the last one you could get is you could get a 6, 1, a 6, 2, a 6, 3, a 6, 4, a 6, 5, or a 6, 6. And there's all of your outcomes. And the reason I like to write it this way is I can now see if I come up this diagonal here. So come up this diagonal right along here. Notice these numbers 1, 6, 1, 5, 2, 4, 3, 3, 4, 2, 5, and 1, 6 all add to 7. So if I want to know sum of 7, there's my sum of 7. I can go 1, 2, 3, 4, 5, 6, and there are 36 outcomes in the sample space. So if you write it this way, you can easily see your sums quite nicely just up the diagonal. Like this diagonal here is 1, 5, 4, 2, 3, 3, 2, 4, and 1, 5. Those are all the sum of 6s. Here's the sum of 2, sum of 3, and so forth.